Hi, this is Dr. Max Boachi, one of the editors of this book. This is a video summary for chapter 26, written by Dr. Daniel Drazen. The chapter title is Deformity Prevention and Correction Strategies. Here are the learning objectives for this chapter. First, we want to understand how deformity can be corrected. And second, we want to understand the in vivo strategies for correcting deformity. And then third is to understand the 3 or 4 point bending forces that are used to correct deformities. And then a final is to go over various deformity strategies in specific scenarios. One or a combination of two fundamental techniques can be used for deformity correction. First is implant force and bending moment application that brings the spine to the implant. And the second is implant force and bending moment application with in vivo implant configuration alteration techniques. Implant forces, when bringing the spine to the implant, can be applied along any of the 3 axes of the Cartesian coordinate system. They're usually applied in the sagittal plane of the spine. However, they can also be applied in the other planes, for example, in scoliosis correction or prevention. Implant contouring includes derotation or application of intrinsic implant bending moments. The figure shown here illustrates the concept of bringing the spine to the implant. The forces that are oriented along any axis or plane may be used A, in the long axis, B, in the sagittal plane, or C, in the coronal plane. The arrows depict applied forces to the implant. The bending moments applied in the sagittal plane are usually of a 3 or 4 point bending or an applied moment arm, and these are described a little bit later. The next figure shows that implant force application by in vivo alterations of the implant configuration. In A, we see an example of implant contouring in vivo. In B, we see intrinsic implant bending moment application about the long axis of the spine. This concept is called derotation. And C, we see an example of an intrinsic implant bending moment application about an axially oriented axis of the spine. Once again, the arrows depict the forces that are applied. The next figure shows additional methods of deformity correction. Distraction, a force applied along the long axis of the spine, can be used to correct A, compression deformations, B, coronal plane translational deformations, and C, sagittal plane translational deformations if enough ligamentous integrity is present. In the next figure, we illustrate bending moments applied in the sagittal plane by A, a 3-point bending mechanism, and B, an applied moment arm cantilever beam. Applied moment arm cantilever beam constructs are generally applied either through flexion or extension bending moments. They can be used with or without distraction or compression or an accompanying dural sac decompression and or interbody graft. These factors are important to consider if an optimal construct design customized to a given clinical situation is to be used. For example, if extension and distraction without an accompanying interbody fusion are to be used, Large screws must be employed to withstand the applied axial loads. In these situations, the use of distraction and extension is followed by ventral decompression, the placement of an interbody weight-bearing graft, and compression of the construct onto the ventral graft. This results in load sharing of the graft. In the figure, we see that the sagittal plane applied moment arm cantilever forces may be applied with either A, flexion, or B, extension bending moments. The straight arrows depict the forces, the curved arrows depict the bending moments. The next figure illustrates what can go wrong if this is done without an interbody fusion. It may be associated with a suboptimal success. By adding the interbody graft as shown, this permits the minimization of the complication. The next figure illustrates the next type of technique to correct kyphotic deformity. This is the crossed rod technique. This is a well-established method of thoracic and lumbar kyphotic deformity correction. Regardless of the construct type, the technique involves the simultaneous application of deformity reduction forces to the spine by means of moment arms. Gradual reduction is thus achieved via a 3-point bending force application mechanism as shown in this figure here. The next figure shows an example of 3-point bending constructs. It's very important to understand this concept. A 3-point bending construct brings the spine to the implant via a dorsal approach in the first figure on the top left. This is further illustrated by an example of a cervical deformity and subsequent ventral deformity correction by bringing the spine to the implant by sequentially tightening the intermediate screws of a ventral cervical plate, thus applying the 3-point bending forces. The figure C illustrates the concept of terminal 3-point bending construct. This is a 3-point bending construct which simply has one long and one short moment arm. For terminal 3-point bending constructs to be effective in reducing translational deformation, they must be applied properly as illustrated in this figure. The long arm of the construct must be placed A, caudally with a ventral translational deformation, and B, rostrally with a dorsal translational deformation. The next figure compares 3-point versus a 4-point bending forces. The 4-point bending of the spine, as defined by White and Punjabi, involves loading a long structure with forces on one side, transverse forces on one side, and 2 on the other. The bending moment is constant between the 2 intermediate points of force application if all forces are equal, whereas in the 3-point bending, the bending moment peaks at the intermediate point of force application as shown in the figure. So to summarize, in a 3-point bending construct, a force or load is applied to the spine at 3 distinct points. This setup consists of 2 points applying a downward force, while a third, position between the 2, supports the spine. The middle point acts as the fulcrum or pivot. The 2 outer points create the bending moment that produces the flexion or extension of the spine, depending on the orientation of the forces. In a 4-point bending construct, the force or load is applied to the spine at 4 distinct points. 2 points apply downward forces, while the other 2 positioned between the outer points support the spine. This creates a more complex loading condition compared to 3-point bending. It's important to also understand the reversed 3-point or reverse 4-point bending. That construct is illustrated in this figure here. This is a 3-point bending force, dorsally directed force at the fulcrum, and can be used to reduce spondylolisthesis. The next figure shows the technique of a short segment parallelogram deformity reduction. This can be used to reduce a lateral translational deformity as shown in this figure. Pedicle screws are placed. The pedicles are then connected by rods as shown, and the rods are connected, and a torque is applied to both rods simultaneously with rod grippers. In this figure D, the technique illustrates how this is used to reduce a lateral L4-5 dislocation. Once the dislocation is accomplished, reduction can be maintained using a rigid cross fixation as shown, and the distraction can be maintained using placement of an interbody bone graft. The next figure shows the example of in vivo rod contouring. This can be used to alter spinal alignment from a pathological kyphotic curvature with the rods configured to match A, the curvature of the pathological spine, to B, the desired alignment. The final figure illustrates the final technique to correct deformities. Here we see the technique of spinal derotation. Spinal derotation is accomplished by careful simultaneous rotation of two rods that have been attached to the spine in its deformed scoliotic state. The rotation of the rods by 90 degrees converts A scoliosis to B, a kyphosis. If the resultant kyphotic deformity is unacceptable, it may be corrected by rod contouring as illustrated in the previous figure. This strategy can also be applied to biconcave curves, as shown in figure C and D. So in this chapter, we went over some of the main techniques for deformity correction. We've seen examples of bringing the spine to the implant. We've seen the use of different strategies to correct deformities, including 3- and 4-point bending constructs, in vivo contouring. We hope that this has given you a good understanding of strategies so you can use to correct both deformities in the coronal or sagittal plane. Thank you.